Carnegie Climate Governance Initiative. I'm Nick Harrison, and for those of you not familiar with the Carnegie Climate Governance Initiative, we're a time-limited foundation-funded initiative of the Carnegie Council for Ethics and International Affairs. And C2G Learn is one of our series of online events that we convene to catalyze learning about climate-altering approaches and their governance. And you can access recordings on many other topics through our website on 3Ws, c2g2.net, and click on the C2G Learn button, and you can explore more content there. So today we're going to learn more about how the Working Group 1 report of the Intergovernmental Panel on Climate Change Sixth Assessment addresses carbon dioxide removal and solar radiation modification, and explore what, if any, implications this might have for governance. Now, this Working Group 1 report is the first of several reports, more coming out this year. And the latest report that was published last year addresses the physical science basis of climate change. Now, almost 4,000 pages, there's a lot to take in. So I'm delighted to welcome today three distinguished professors to help us on our learning journey. These three speakers are among the many international authors that contributed to this report, and it can help us to better understand what it tells us about CDR and SRM. So if our guests are now on the screen, if I'd like to just briefly introduce our three guest speakers. Firstly, in no particular order, we've got Professor Yuri Rogel from who's joining us live from London. Yuri is Director of Research and Reader in Climate Science and Policy in Imperial College London, and a Senior Research Scholar at the International Institute for Applied Systems Analysis. He's a lead author of Working Group 1 AR6, and also was a coordinating lead author of the special report on 1.5 degrees global warming, was published in 2018, and the previous Fifth Assessment report. He's also a consummate lead author of the United Nations Environment Programme's Emission Gaps report. And welcome, Yuri. Second up, we have joining us from Vancouver in Canada, Professor Kirsten Ziegfeld, who's Distinguished Professor of Climate Science in the Faculty of Environment at Simon Fraser University in Vancouver, British Columbia. Also a lead author of the Working Group 1 Sixth Assessment, and a lead author of the IPCC's special report on 1.5 degrees as well, and a contributing author in the fifth and third assessments too. Welcome, Kirsten. And thirdly, joining us later at night from Bangalore, we have Professor Gobsami Bala, who's professor at the Center for Atmospheric and Oceanic Sciences at the Indian Institute of Science. And he's published over 100 peer-reviewed journal papers on climate change and the carbon cycle. Main interests in research cover modeling of climate change, climatic effects of land cover change, and climate engineering. And Bala is also a lead author for the Working Group 1 contributions to both the AR6 reports and AR5 reports. So welcome, Bala, and thanks very much for joining us, guests, and those joining us live for the webinar. So let's get started. We're going to begin today with presentations from each of our speakers, which conveniently have been pre-recorded, so you can watch them again at your leisure if you miss anything or you have to pop out for a coffee halfway through. And then we'll reconvene once again with our live speakers, experts here for a Q&A session. So whilst you're watching presentations, feel free to start adding any questions you have for the speakers in the Q&A box at the bottom of your screen, and then we'll try to get through as many of those questions as we can in the time that we have. So I think I'll now ask my colleagues, to please start the presentation, and over to our speakers.
Hello. The reports of the Intergovernmental Panel on Climate Change, or IPCC, provide key scientific evidence to the international climate negotiations. Today, in this presentation, I want to look together at what the future projections and pathways that are used in the Working Group 1 report of the Sixth Assessment report of the IPCC tell us about the Paris Agreement long-term temperature goal. Starting with the Paris Agreement long-term temperature goal, which is to hold the increase in global average temperature to well below 2 degrees and to pursue efforts to limit it to 1.5. This global temperature goal has been further strengthened, or has received an even stronger focus on 1.5, during COP26 in 2021 in Glasgow, where the decision was to resolve to pursue efforts to limit the temperature increase to 1.5. So this provides us with very clear global context as to what the international climate negotiations are aiming to achieve. What information does the IPCC provide us to inform what is necessary to achieve these goals? First and foremost, here I draw on one of the figures of the summary for policymakers of the IPCC latest Working Group 1 contribution to the Sixth Assessment report, and which shows the near linear relationship between cumulative emissions here on the horizontal axis and global mean temperature increase on the vertical axis. And what this really shows is that every ton of CO2 emissions that we emit into the atmosphere adds to global warming. And the figure shows that this is true both for the historical period on the left-hand side of the graph, as well as for projections under a variety of scenarios, to which I will come back later. Here you can see that depending on the cumulative emissions that we emit until 2050, we would end up around 1.5 or around 2.5 degrees of warming. So from a physical science perspective, limiting human-induced global warming to a specific level requires limiting cumulative CO2 emissions, which means that we need to reach at least net zero CO2 emissions, along with strong reductions in other greenhouse gases. From this near linear relationship that we see here on the left, we can then also draw more quantitative implications. And this is what was carried out in this table that is also from the summary for policymakers of the IPCC report. And it really shows that we know what needs to be done to meet the goals of the Paris Agreement. Starting at the top of this table, we see that current warming of around 1.1 degrees has been caused to a large degree by the historical emissions from 1850 to date, of which there were roughly 2,400 billion tons. At the same time, the lower end of the table then tells us what needs to happen in the future if we still want to limit warming to 1.5 or other temperature limits. So let's focus on 1.5. Given where we are today, that gives us, for a 50% probability of limiting warming to 1.5, a remaining carbon budget of about 500 billion tons of carbon dioxide, starting to count from the beginning of 2020. For context, currently we are emitting around 40 billion tons of carbon dioxide annually into the atmosphere. If we think that a 1 in 2 chance of limiting warming to 1.5 degrees is insufficient, then we would go to higher likelihoods and thus lower carbon budgets. In the same way, if lower probabilities are acceptable or lower likelihoods, we would look at the left-hand side and have slightly larger budget. Importantly, any of those numbers can also be higher or lower by around 220 billion tons of CO2, which is a sizable chunk for carbon budgets compatible with 1.5 degrees, depending on how successful we are or how unsuccessful we are in reducing non-CO2 emissions, including methane, nitrous oxide, and fluorinated gases. The IPCC report doesn't only calculate carbon budget, but also uses emission scenarios. And it uses these emission scenarios as tools to understand our global future. And these figures here show the core set of 5 illustrative scenarios that have been used throughout the IPCC Working Group 1 report to illustrate how future climate change depends on our choices and our emissions over the coming decades and the rest of the century. Here on the left-hand side, in the large panel, you can see the evolution of global carbon dioxide emissions. The scenarios are labeled with their scientific labels. In more accessible terms, these scenarios are referred to as the very high, high, intermediate, low, and very low scenario, respectively. You can also see here on the right-hand side, and this is just a selection, that these scenarios do not include only carbon dioxide emissions, but also assume accompanying evolutions of non-CO2 greenhouse gases and aerosols. For example, here at the top, you can see the methane evolutions that go with the scenarios on the left, and also nitrous oxide and sulfur dioxide. What do these scenarios imply for global warming? This figure shows the global warming projections, or both historical and then projections of those 5 scenarios. And what you can see is that over the first decades, these scenarios don't distinguish so strongly in terms of absolute temperatures, although the rate of warming differs quite significantly. And by the end of the century, there is a spread of almost 3 degrees between the lowest and the highest scenario. Looking a bit more in detail to the numbers and the quantifications of the temperature outcome of these different scenarios, we can look at table SPM1 of the summary for policymakers, where this information is highlighted. First and foremost, I think it is really important to see that in the near term, all scenarios, the best estimate is that they will reach 1.5 degrees. At the same time, there is a very important difference between what happens afterwards. In the lowest scenario, 1.5 degrees is reached, but warming doesn't continue to increase significantly thereafter. By mid-century, there is still an important probability that warming might still be below 1.5, while the best estimate is 1.6. And by the end of the century, because of the assumed carbon dioxide removal, net global carbon dioxide removal in those scenarios, warming has been reversed slightly, with now a best estimate of 1.4. In all other scenarios, you can see a continued increase in warming until the end of the century, with the intermediate, high and very high scenario already having a best estimate of 2 degrees of warming by mid-century, and well beyond 2 degrees by the end of the century. So what do these illustrative pathways of the IPCC report tell us for the need for carbon dioxide removal? In essence, not very much yet. These illustrative pathways span a range of very high to very low emissions, but they do not show the variations in CO2 removal strategies that could be applied to achieve the lowest pathway and that have been identified in the literature. And here on the left-hand side, you can see the same figure of the Working Group 1 SPM. And on the right-hand side, I have now added a snapshot of the special report on global warming of 1.5 degrees. And to first order, on the right-hand side, particularly the pathways shown by P1, P2, and P3, show alternatives for how this very low scenario of Working Group 1 could be achieved. And on the right-hand side, it shows fossil fuel and industry emissions and their reductions in gray, the contributions of agricultural, forestry, and land use emissions in brown, and then the contributions of bioenergy with carbon capture and storage, or BECCS, in yellow. And what you can see if you look at the pathways P1, P2, P3, is that the relative contributions of these different measures varies significantly in these different pathways. And that means that there are key strategic choices to be made about how much carbon dioxide removal and which type of carbon dioxide removal is used to follow a pathway that is consistent with limiting maximum warming close to 1.5 degrees C, and in line with the long-term global goal of the Paris Agreement and the strengthened emphasis on 1.5 of the Glasgow Climate Pact.
This presentation explores how the Working Group 1 report of the IPCC addresses carbon dioxide removal. Carbon dioxide removal in this report is assessed in 2 chapters. Chapter 4, which is the chapter about future climate projections. And this chapter focuses on the climate response to carbon dioxide removal, or CDR, and the termination effects of CDR. Whereas chapter 5, which is the chapter on carbon and other biogeochemical cycles, looks specifically into the carbon cycle response to CDR and addresses aspects such as the effectiveness of CDR at drawing down atmospheric CO2, the asymmetry in the carbon cycle and temperature response to carbon dioxide emissions and removals, and the effect of specific CDR methods on climate and biogeochemical cycles. The figure to the left illustrates the response of atmosphere, land, and ocean carbon stores to 100 billion metric tons of carbon, which corresponds to about 370 billion metric tons of carbon dioxide removal from the atmosphere. And this figure illustrates that after the removal, the atmospheric carbon dioxide concentration declines very rapidly and then rebounds within a few years of the removal. And this rebound is due to loss of carbon dioxide from the land and from ocean carbon reservoirs. And this illustrates that only a fraction of the CO2 removed remains out of the atmosphere. This fraction of CO2 removed that remains out of the atmosphere is a measure of CDR effectiveness. And it is not a constant number, but it depends on the atmospheric CO2 concentration from which CDR is applied, and also on the magnitude of the carbon dioxide removal. So this is illustrated, for example, in this upper panel here, which shows the fraction of carbon dioxide that remains out of the atmosphere after removal as a function of the CO2 concentration from which carbon dioxide removal is applied. And what we see here is that as the CO2 concentration decreases, the fraction that remains out of the atmosphere, or in other words, the effectiveness of carbon dioxide removal decreases as the atmospheric CO2 concentration decreases. It also shows that there's a slight dependence on the magnitude of removal. So here these triangles indicate a smaller amount of removal, whereas these squares here indicate a larger amount of removal, indicating that the effectiveness decreases slightly with the amount of removal. The report also addresses the asymmetry in the carbon cycle response to CO2 emissions and removals. So this figure here shows the fraction of carbon dioxide emissions that remain in the atmosphere after an emission. So this is shown here to the left of this graph. And here to the right, it shows the fraction of CO2 removals that remain out of the atmosphere after a removal. And these different symbols, they indicate a range of Earth system models. And so what is shown here, that the fraction of CO2 emissions remaining in the atmosphere after an emission is larger than the fraction remaining out of the atmosphere after a removal, implying that CO2 emissions are more effective at raising atmospheric CO2 than CO2 removals are at lowering atmospheric CO2. And for these models shown in this figure, this asymmetry ranges from 2 to 9%. So the results presented so far were based on idealized model simulations, where it was assumed that carbon dioxide is removed from the atmosphere and permanently stored in the geologic reservoir. But another part of the chapter also assesses the effect of specific CDR methods on climate and biogeochemical cycles. So here, these different rows, they correspond to different CDR methods, which range from land-based methods such as afforestation, for example, or soil carbon sequestration, to ocean methods such as ocean iron fertilization or ocean alkalinization, and then to some more technological or engineered methods such as direct air capture and storage. And the core of the Working Group 1 assessment focuses on the biophysical effects of these methods. So biophysical effects are effects on evapotranspiration, for example, or on the reflectivity of the Earth's surface, which is referred to as albedo, which in turn affect the temperature at the surface, and on biogeochemical effects, which are related to emissions of greenhouse gases such as nitrous oxide and methane, for example, or in the ocean on effects such as ocean acidification. And it also assesses how these biogeochemical and biophysical effects then feed back on the carbon sequestration potential of each of these CDR methods. And then for completeness, we also show the sequestration potential of these CDR methods and potential co-benefits and trade-offs with other societal goals that are related to water quality or food supply, for example. And a detailed assessment of the sequestration potential and these co-benefits and trade-offs will be done by the Working Group 3 report. And really what this figure here illustrates is that all CDR methods have a range of side effects on biogeochemical and biophysical cycles that could either amplify or weaken the climate benefit of these CDR methods. In chapter 4, the climate effect of emission scenarios with net negative emissions is also assessed. So in this example here, the climate model responds to an idealized scenario with atmospheric CO2 concentration rising to 4 times CO2 and then declining back to pre-industrial levels as shown. And then these different curves here in the upper left panel, they show different climate variable. And what this figure here illustrates that the changes in these variables lags behind the decline in the atmospheric CO2 concentration that is induced by net negative CO2 emissions. And now some conclusions. CDR results in a drop in atmospheric carbon dioxide concentrations as intended, but not all of the CO2 removed remains out of the atmosphere, because the CO2 that is removed is partly replaced by release of CO2 from the land and the ocean. Also, the effectiveness of CDR at drawing down atmospheric CO2 is not constant, but decreases with decreasing atmospheric CO2 concentration from which CDR is applied and increasing amount of removal. The asymmetry in the carbon cycle response to CO2 emissions and removals implies that offsetting a CO2 emission with an equivalent CO2 removal could result in a different climate than avoiding the CO2 emission in the first place. And finally, most CDR methods have effects on climate and biogeochemical cycles that could either amplify or reduce the climate benefit of CO2 sequestration by CDR methods. Thank you.
Good morning, good afternoon, and good evening, depending on where you are located and watching this presentation. First, let me thank the organizers, C2Z, for organizing this outreach event, and Nick for moderating this session, and Rogel for your very nice presentation on the future emission pathways, and Kristen for your wonderful presentation on carbon dioxide removal methods. And your, these two presentations have provided an excellent background for my presentation on solar radiation modification. So following is the outline for my presentation. First, let us, we will discuss what is, SRM, and also what are the various options. Then we discuss the chapters that assess SRM. Then the key take-home messages on SRM from the Working Group 1 IPCC report. So this is the IPCC glossary definition of SRM. There are two key aspects related to SRM that should be, we should remember that. One is, SRM is not at all related to greenhouse gas mitigation. So it doesn't involve emission reduction, and also it does not remove carbon dioxide removal. It rather involves reducing the amount of incoming solar radiation reaching the surface. So we'll see the various options, how they do this reduction in incoming solar radiation. There is also one option involving the high-level cirrus clouds that affects the long-wave radiation budget of the planet. But interestingly, this option has been classified as SRM both in this particular IPCC report and also the previous IPCC report on the special report on 1.5 degrees C. So here is the schematic that illustrates the various SRM option. The first one is the space sunshade. So in this particular case, the proposal is to place a very big mirror or multiple mirrors or highly reflecting small particles in between sun and earth in space. So this would reduce the amount of incoming solar radiation to the planet. And the next option is stratospheric aerosol injection. So this is the most widely studied option at this time. So this option would involve injecting sulfate aerosol particles into the stratosphere, where these particles would reduce more sunlight back to space and thereby cool the planet. The third option is MCP, marine cloud brightening. Here, the idea is to inject sea salt aerosols into the marine low clouds. These clouds are usually found along the west coast of the continent. And finally, ground-based albedo modification. So in this particular option, the proposal is to increase the reflectivity of either the ocean surface or the land surface. In the case of ocean, you can place highly reflecting foam particles, or you can also produce micro bubbles at the surface of the ocean. And then over the land, you could either bioengineer the crops so that the crops leaves are lighter color, and light colors basically reflect more sunlight back to space. And also, in the urban areas, one could paint the roofs white, because the roofs, white roofs are more reflective compared to darker color roofs. Even though there are five options that I showed earlier, the current IPCC report focuses on three aerosol-based SRM options. The three options are SAI, MCB, and CCT. So basically, as I already indicated, CCT involves reducing the amount of high clouds, and thereby, which allow, their reduction would allow more IR emission to space and thereby cool the planet. So these are the chapters that assess the SRM. In chapter 4, the climate system response to SRM is assessed. And in chapter 5, the carbon cycle response to SRM is assessed. In the case of chapter 6, the cooling potential of these various SRM options are assessed. And in the case of chapter 8, which deals with water cycle, the water cycle response to SRM is assessed in chapter 8. There is also a very nice discussion in a box on SRM in the technical summary of the report. But interestingly, there is no mention of SRM in the SPM, which is basically the summary for policymakers. So following are the key messages on SRM from chapter 4. First, SRM could either fully or partially offset the global warming, global mean surface temperature change, but the offset would be imperfect, particularly on regional and seasonal scale. And there also could be several side effects, including ocean depletion in the stratosphere and the corresponding increase in harmful UV radiation at the surface. And also there could be altered regional rainfall pattern because of SRM. And also there is one more effect of side effect of SRM, which could be very harmful. This is called the termination shock. So I haven't slide separately for a termination shock. We'll come to that later. So one of the key messages is that there have been several improvements in modeling of the SRM SAI option since the last IPCC report in 2013. And one of the key results of this modeling improvements is that multiple temperature-related goals, such as global mean surface temperature change equated to pole temperature gradient and the temperature difference between the northern and southern hemisphere. If there are changes in these three quantities because of climate change, we can actually bring back all these three quantities simultaneously to any level that we want. So this has been studied for the SII options using climate models. And finally, a sober note that large uncertainty from our incomplete understanding of various physical processes, specifically the interaction between clouds and the aerosols related to SRM options. So these uncertainties, of course, are not only unique to modeling the SRM options, this also is relevant to the projection of future climate change. So the next message is from chapter 6, which assesses the cooling the cooling potential of the various SRM options. So it finds that the aerosol-based options could provide cooling that could potentially offset a warming from doubling of atmospheric CO2 concentration, and with the SII at the higher end and CCT in the lower CCT with the lower potential. Next, specifically MCB and the CCT, they involve interaction with the cloud, and because of that, there is large, low confidence in the effectiveness of these two approaches. And here is a message from chapter 5. If you remember, SRM causes cooling. So because of this, more carbon can be stored in the atmosphere and the ocean, and because of that, the atmospheric CO2 could be slightly reduced by SRM. However, because this CO2 change is very, very little, ocean acidification problem would continue under continued CO2 emissions. And here is a final message from chapter 8. So it says that the abrupt introduction or termination of SRM would cause abrupt climate and water cycle changes. So here is the message on termination. So we need to first remember that SRM is a mask to the climate change problem. It does not really address the root cause of the climate change problem, which is basically the increase in greenhouse gases in the atmosphere. If the mask is abruptly removed for any reason, very severe climate change could happen. That is, rapid climate change on the order of several degrees per decade could occur, which could subject human and natural ecosystems to severe climate change. I mean, you can just compare this very large rate to the current rate, which is about a few tenths of a degree per decade. Now, what do we expect in the next two the reports that will be coming in this year, 2022? So first, I think first is let's look at what is covered, what is going to be probably discussed in working group 2. So SRM is going to involve risks and benefits to human and natural ecosystems. And so working group 2 is going to assess these benefits and risks of SRM. And also, because SRM involves Because SRM involves risk, it needs a formal governance framework. So working group 3 is going to assess the international governance of SRM. So this governance framework is expected to cover basically the research as well as possible deployment of SRM. And with that, I conclude my presentation. Thank you for watching.
Okay, hello, welcome back. Thanks for the presentation, speakers. And if I could be joined once again by our live speakers in Vancouver and London and Bangalore. Thank you, Jury, Kirsten and Bala for joining us once again. So I understand some of the slides may have been a bit blurry at times for some of the viewers. So have no fear, all the presentations and the slide decks will be available on the website. My colleagues will share it in the chat link here, and you can always contact us directly afterwards if you can't find them. They'll be on the C2G Learn. Just follow to the page of the IPCC related content, and you should be able to find it soon after this event from tomorrow onwards. Now, we're going to pivot to a Q&A session. We've got a tremendous resource here, 3 very experienced experts. And this is your opportunity to pose some questions to them to help clarify all our understanding, very complex issues. Also, we're dealing with 2 largely quite different in many respects areas here, so carbon dioxide removal and SRM, obviously very different, large uncertainties around them in many cases. So we'll try to distinguish between the 2 as we go through the questions. We've had one question already in the Q&A. Remember to press the Q&A button if you want to ask a question, and we'll take them from the top. Actually, we had the very first question was in the chat. Please don't put your questions in the chat. Try and put them in the Q&A so we don't lose them. And perhaps we'll start off with this first one for whoever'd like to take it from the panel. This is from Stephen Salter, who says that aiming for 1.5 degrees C implies that the present conditions are acceptable. So why do we not want to fund research on ways that might get us down to 0? Good question. More a political as well as a scientific question, perhaps. But who'd like to take that? Yuri, would you like to give that first go?
Yeah, happy to answer that question. And I think the research for answering that question is already being carried out. And has already been assessed in the IPCC latest assessment report. I mean, we understand that from a geophysical perspective, if we achieve net negative CO2 emissions, we will be slowly reversing some of the warming. We won't be reversing all of the aspects of climate change, some aspects of sea level rise, some aspects of also in the carbon cycle might not be reversed on time scale of centuries to millennia or even never. But ultimately that research is ongoing. Why are we focusing on 1.5? Of course, that is because the countries, the joint countries of the UNFCCC have decided that is the lowest limit in their international target. That ultimately is not a scientific question to be answering.
Quite right. Thanks, Jerry. I don't know whether Kirsten or Bala want to add to that, but I think that's a fairly succinct answer there. If I might pick up on something you mentioned there, Yuri, onto another question, this concept of net negative. Now, for some of our viewers that are not scientists that come from more the policy community, they will have heard a lot more about net zero. We've all heard net zero all over the place for the last year or so. The drum roll has been intensifying, particularly around the Glasgow COP at the end of last year. Can you tell us any more? Can any of you tell us more perhaps about what role does CDR or this carbon dioxide carbon removals have to play in reaching net zero? What exactly is the role? Is it even possible to get to net zero without CDR? And indeed, net negative, what's the relationship? Is there a way you could explain that fairly succinctly to some of our viewers that might be a little lost with what net zero means in terms of actually what might need to be done or what decisions might need to be addressed? Who'd like to take that?
I could also start off, and I'm happy to hear additions by Kirsten and Bala. We have to be clear about what is first and foremost, why are we talking about net zero targets? And that is because we have now established that every ton of CO2, or scientifically established that every ton of CO2 that we add to the atmosphere adds to global warming. And that means that if we want to stop global warming from further increasing, we have to stop adding CO2 to the atmosphere. There are two ways of doing that. One is to stop emitting or just stop doing any interactions with CO2, stop emitting and stop removing it, and then there is no net effect on CO2, or we remove exactly the same amount as we would still be emitting. And that is where that net zero comes from. And although that is not really part of the research that is being assessed or the science that is being assessed in Working Group 1, the 1.5 degree special report of the IPCC, now published 4 years ago, and showed, and I now showed also in my presentation, is that there are different strategies that can be pursued societally to reach that net zero goal. They all involve strong reductions in CO2 emissions, and somehow they all involve some degree of some sort of carbon dioxide removal. How much of it, which types, where and how, these are still kind of policy and societal questions to be answered. But scientifically, all scenarios, all pathways that are out there at least use some degree of carbon dioxide removal. In some cases, that is just from natural sources, and in many cases, it's also to some degree from technological sources, such as bioenergy with carbon capture and storage, or the direct air capture that Kirsten also referred to in her presentation.
Great, thanks, Yuri. Unless Kirsten or Bala want to add to that, I think let's move on to another question. This is from Fernando Tudela, and perhaps this is one for you, Kirsten. Don't you think there's been an overconfidence in relying on planting trees as a prevailing strategy in many developing countries for dealing with climate change? This perhaps speaks to some of the content of your presentation. Any thoughts on that?
Yeah, so the enthusiasm for planting trees, both in regions where there were no trees before, which we call afforestation, or replanting trees in areas where they have been removed, which we call reforestation, comes from the potential to sequester carbon dioxide through these methodologies. So research has shown that by 2030 we could remove around. So this is we could remove up to about 10 gigatons of carbon dioxide globally by planting trees. So this is so the question that is posed here is a very broad one, and I'll answer that from a Working Group 1 perspective, because many of the government's implications and also the regional implications are not addressed in our report. They're addressed in the Working Group 3 report. So what I can say about afforestation from a Working Group 1 perspective is that first of all, yes, trees do sequester carbon dioxide from the atmosphere, but they do also alter the surface energy balance. So they are dark. Trees are generally darker than a bare soil. So when we plant trees, we reduce the albedo of the Earth's surface, and so we reflect less incoming solar radiation, which could lead to local or regional warming. So in fact, research has shown that if we afforest or reforest at mid to high latitudes, we might get a net warming effect. So from a climate system perspective, there are certain regions where afforestation from a climate perspective is actually not very effective. Things change a little bit if we look at low latitudes. So especially in tropical regions, it has been shown that because the albedo effect is smaller, and also there's an increase in evaporation, that actually these effects compound count the CO2 sequestration. And so this is why, at least from a climate science perspective, the tropical regions seem to be the better locations to actually look at tree planting in terms of climate effectiveness. Then obviously there are many government's implications on the ground that have to do with socioeconomic conditions in those countries, but those are actually not addressed in the working group 1 report. So just to summarize, when we talk about afforestation and reforestation, we should not only consider the CO2 sequestration potential, but we really need to take these other potential climate effects into account, which in some regions could counter the benefit of planting trees.
Great, thank you, Kirsten, for a helpful answer there. If I might tag on another question here, which was from Chris Vivian. It's more of a speculative question, but it's in a similar kind of vein. What if you removed CO2 from the ocean at the same time as from the atmosphere at a rate so as to maintain the equilibrium between them? Would this not reduce the rebound of CO2 back into the atmosphere from the ocean? That one of the mechanisms that you were referring to?
Yeah, that is correct. What is really driving the outgassing or the release of carbon dioxide from the ocean is the imbalance between the ocean and the atmosphere. So if there's more ocean, if there is more carbon in the ocean than there's in the atmosphere, then there would be a flux out of the ocean. So yes, it is correct that if we were to manage to remove carbon dioxide at the same rate from the atmosphere and the ocean and keep that gradient constant, then likely we wouldn't see that rebound. However, in effect, what is happening is that the ocean has its own time scales. So the ocean circulates, and those time scales, so depending on the processes that we're looking at, they vary from years to actually many centuries to millennia. And these time scales really influence the response of the ocean. So designing intervention in such a way that we could achieve the same rate of removal would be very tricky. And this is also because we have the land involved at the same time, right? So as we change the concentration in the atmosphere, the land will also respond to that. So to engineer the system in such a way to prevent rebound is very tricky because of these various timescales involved.
Thank you. Thanks very much. Now, if I might, there's a question here directed specifically to Jerry, and then I want to move on and address a question to Bala afterwards on moving on to the topic of solar radiation modification. But first, Jerry, a question from Ulrika Arnio. Ulrika, I hope I pronounced your name correctly. How are the non-CO2 now assumed to develop in the budget calculations, to decrease or increase? So what about permafrost melt and methane clathrates? I'm not sure what clathrate is, maybe you do. Are there impact included? So is the impact of this permafrost melt included in the budgets?
Yeah, so the short answer is yes. So the question refers to two types of emissions. One are the human caused emissions. So if we emit more methane in the future, then there is less space for emitting CO2. And that kind of trade-off is taken into account by assuming also equally strong reductions in methane that are consistent with the transformation to a net zero CO2 world. But there is variation. I highlighted that depending on how successful or unsuccessful we are in those reductions of those human caused methane emissions and other greenhouse gas emissions, carbon budgets might be higher or lower by 220 billion tons of CO2 or more even. Yeah, might vary. Then the emissions that come from permafrost are also taken into account through a different term in our estimation. So again, to conclude, yes, those factors are taken into account as uncertainties in the budget calculations.
Thanks, Jerry. Anyone want to add to that? Or I think that covers it quite nicely. If not, let's move on to a question from Miles Perry. And Miles asks, and perhaps this one for you, Bala, what are the major knowledge gaps in SRM? So, and also a question to all the panelists, what do panelists think of the argument that SRM is so inherently dangerous that there shouldn't even be research into the topic? So Bala, perhaps you'd like to start us with that one. Oh, I think you're muted, Bala. I can't hear you at the moment.
Sorry about it.
Great, we can hear you now.
Fine, thank you. I don't know whether we could call this as a knowledge gap, but I would rather put it as uncertainty. First of all, the uncertainty in quantification of even at the global mean level, how much cooling, a certain amount of aerosol can cause. I think there is large uncertainty, which is mainly coming from, in the case of SAI, it comes from the aerosol microphysics, the stratosphere. But in the case of other two aerosol-based schemes, such as MCB and CCT, the aerosols actually interact with the clouds. And we all know that, this is not just for SRM, but even in the case of, projection of climate change, the aerosol cloud interaction, aerosol cloud and radiation interaction, provides one of the largest uncertainty. So mainly there is large uncertainty in this, but then, because of this, this uncertainty is in fact, much larger when you look at the regional scale as well as seasonal scale. And, and also you could actually have even, when you exactly compensate climate change at the global scale, that could be large regional and overcompensating effects at the regional scale. So, how much that is, I think that's where the biggest uncertainty is.
Great, thanks, Bala. And the second part of Miles's question to any of the panelists, what do you think of the argument that SRM is so inherently dangerous that there shouldn't even be research into the topic? Anyone like to respond on that? Or not strictly a science question, but perhaps it is. Yeah.
I'm happy to respond.
Sure.
Yeah. Yes, I do think that it is important to do research in it, and I think, and there are two reasons for that. First, just at face value, SRM sounds so simple and so simple and almost too good to be true. And it's only with the additional research that we have put into them into it that we understand the risks for the hydrological cycle, for regional and seasonal changes. So that research was really important to identify those risks, because otherwise it might have looked much more safer than what we now know it is. A second reason why we should be researching it is that SRM has this very particular characteristic that it can basically be deployed by a single large actor. It is not so expensive, and it doesn't really require global cooperation. And so really understanding those consequences from a scientific point of view are essential.
Thank you, Yuri. Kirsten or Bala, would you like to make a respond on that, or should we move on?
Yeah, maybe I can just very quickly add to that under the SRM umbrella, there are very different approaches as Bala showed, right? And there are these large-scale engineering approaches such as aerosol injection, modification of clouds, but then there's also more local interventions which have to do with changing the albedo of the Earth's surface through crop engineering or thinking about urban surfaces and so on. And I think so we also have to make a distinction between different types of approaches, and those that are more local are less risky to cause planetary unintended effects.
Thank you, Kirsten. Bala, what does I might ask a further question? Does the report address this relationship between SRM and these other climate responses, for example, CDR or emissions reduction and adaptation as well? Is there any? Does it address that relationship in any way?
Well, I think the way it was very nicely illustrated. In fact, in SR 1.5, a report in 2018. Basically we know climate change should be addressed using mitigation, which includes emission reduction and CDR. There is also, of course, adaptation, but we all know that we could adapt only to some amount of climate change. When the climate change is large, there is no way we can adapt to it. And emission reduction, in general, mitigation has been really hard. So one instance where SRM, is in fact, I would say advocated, or we talk about using it if in the future, let's say we exceed 1.5 degree for a brief period of time, let's say for a couple of decades, right? So these are scenarios that are called overshoot scenarios, where the temperature basically exceeds either 1.5 degree or 2 degree Paris temperature goals for a very brief, like couple of decades. So, can we use SRM for that very brief period while mitigation, is taking place? So in some sense, let me put it this way, very simply, SRM has been kind of, is suggested as a supplement to deep mitigation in overshoot scenarios. Yeah.
Great, thank you, Bala. We have, if I move on now, I think we have just a few minutes left of the Q&A. There is a question here from Joshua Sarnoff on what would international SRM or CDR governance look like, part of the UNFCCC, what kinds of controls, reporting, risk management? I'm going to defer that question, Joshua, if you don't mind, as this is about the physical science. We will be running further C2G Learns on the Working Group 2 and Working Group 3 reports, where, as I understand it, those kind of topics will be addressed in more detail once those reports are published, unless of course any of the speakers here would like to make a brief comment on that before we move on. Bala, yeah.
I'll just make one statement. In fact, just this week I read a paper where the proposal was to completely ban basically the proposal is to come out with non-use of solar geoengineering. So there are extremes. So right now, there are a lot of discussions, and but I won't comment more than that.
Great. Okay, thanks. And I should say, I'd point you to the C2G website as well, and you can learn a lot more about the governance situation with regards to these. We even have various evidence briefs on these topics as well. So if you want to learn a little bit more about the current situation in the research literature, then check out our website. In the remaining few minutes, I think I'd like to just turn to each of the our speakers in turn and ask about, we've heard obviously the IPCC reports are a tremendous effort, and they're tremendously useful for decision makers and the policy making process to really understand the latest science. And they take a long time to produce, we know that, and they introduce we learn a lot from each one. And thank you for your time today and your presentations. I think I've certainly learned more that I didn't understand, and hopefully our viewers have too. But perhaps before we close the Q&A now, maybe each of you would like to say something about where the gaps are, some of the big gaps that you see perhaps in your specific domain that were flagged possibly in the report, particularly in relation to carbon dioxide removal or SRM. So what do we need to learn more about in future, possibly in successive reports? Mindful that, of course, there's subsequent reports coming out as part of the Sixth Assessment, but if I could phrase the question in a very broad terms like that and give you an opportunity just to mention anything you'd like on that. Could we start with, let's start with Kirsten.
Yeah, thanks. So with regard to CDR, I think we need to understand the climate effect of specific CDR methods a lot better. So what are so really to look at how the entire Earth system responds to those interventions, both in terms of this biophysical effect that I mentioned, but also effect on other greenhouse gas cycles such as methane and nitrous oxide, and because these effects can be potentially significant. So yeah, so that's something we need to understand better. Also, what some of the potential trade-offs and co-benefits are for other societal goals. And then something I'd like to point out is also there's quite a divide between, I think, the scientific community and the policy world. So in the science community, we sort of people are aware of these effects, but actually at the scale of implementations where offset protocols are designed, and there's very little awareness of that. So I would say sort of on the non-science side, really attempts to bridge that science policy divide.
Okay, thanks, Kirsten. Jerry, would you like to go?
Yeah, in addition, I think from the physical science, there is a key research gap on understanding how these CDR or the carbon dioxide removal methods perform under a changing climate in a changing world. With environmental conditions, the land and the nature-based ones, with very different climatic conditions, and I think that is, and also with different disturbance patterns. So I think that is a key research direction.
Great, very good, thank you, Jerry. And Bala.
I think in a much bigger picture, I think I would say we need to understand the risk of climate change with and also without SRM, right? There is also risk to climate change, and then also risk with without SRM. So I think that needs to be understood in a very holistic manner. I'll just come to specifically, some recent developments where this relates to also knowledge gap, particularly in SAI research, right? I think what needs to be understood. I think recently there is a lot of emphasis on the aerosol microphysics, understanding aerosol microphysics. Particularly, it causes, for example, stratospheric warming. Now, this warming actually introduces, let's say, it actually reduces the effectiveness of SAI. It introduces water vapor into the stratosphere, which is another additional greenhouse gas, and it also basically disturbs the stratospheric dynamics. So that needs to be well understood if you do want to understand SAI. In addition, what are the effects of stratospheric SAI on stratospheric ozone, right? I think this is that's an area of a key active research right now. Yeah.
Okay, great. Thanks very much, Bala. And our time is up, ladies and gentlemen. So it remains only to say, so thanks very much to our speakers for today, and for you, the viewers, and for your great questions, and of course the team in the background helping make all this happen. I should say, do visit the website. You can find more information there. There's a dedicated briefing on the Working Group 1 report, and lots of other resources to find out more about this. We're simply trying to signpost. Obviously, C2G is impartial about all these approaches, and you can find more content on the website. So also, once the webinar closes, you'll see a survey that pops up. So we'd encourage you to feedback any comments or criticisms or compliments, willingly accepted, and that'll help us improve our subsequent events going forward. And do join us again later in the year when we'll repeat this C2G Learn for both the Working Group 2 and Working Group 3 reports as they come out. Thanks very much, and join us next time.